So this will be the first lecture out of chapter 23. So we'll have two lectures here. And so this is chapter over carbohydrates. Okay, so carbohydrates are the most abundant class of biological molecules on Earth. They're made primarily through CO2 fixation during photosynthesis. So some of the roles of carbohydrates, they're energy storage in the form of glycogen and starch. Structural components, as we'll see, cellulose and chitin, for example, involved in cell recognition. They're parts of larger biological molecules such as DNA and RNA, so they're components of genetic information, and cofactors, glycoproteins, glycolipids. So obviously one of the huge classes of biological molecules. So since we're now getting into the biochemistry part of organic chemistry, molecules become very big, so rather than me sketch them all out, I've got them in PowerPoint type of presentation instead, just because the molecules are too big to try to draw in an efficient and timely manner. So monosaccharides are carbohydrates that are simple sugars. They cannot be broken down into simpler sugars under mild conditions. So a lot of terminology in this chapter to understand. Oligosaccharides would mean a few saccharides. So for example, a polymer of 2 to 10 sugars that are covalently attached to each other, or polysaccharides where you can have polymers of simple sugars greater than 10 monosaccharides. Okay, so this is a couple of examples of monosaccharides, so some more terminology. So they are polyhydroxy ketones, which are called ketoses. So this would be an example of a ketose. So polyhydroxy, right, they have lots of OHs on them. And that's a ketone, right, because it's a C double bond O between two carbons. Or you could have polyhydroxy aldoses, right? So there's an aldehyde with a lot of OHs on it. So every single carbon's got an OH. They don't have to, but otherwise they would be a derivative of a carbohydrate. So you can have trioses, tetroses, hexoses, pentoses, so that just denotes how many carbons there are. So this has 1, 2, 3, 4, 5 carbons, so that would be ribose would be an example of a pentose. So they are hydrates of carbon. The empirical formula is CH2O. Okay, so one of the fundamental principles of monosaccharides is that they are chiral. So all aldoses with 3 carbons or more are chiral, at least have 1 chiral carbon or more, and ketoses with 4 or more carbons are chiral. So the number of chiral carbons in a ketose is always 1 less than an aldose. And if you remember this formula from the stereochemistry chapter, 2 to the n, where n is the number of chiral carbons. So if there's 1 chiral carbon, there's 2 stereoisomers. If there's 2 chiral carbons, there's 4 stereoisomers, and so forth. And so one of the things to know is this D and L way to name sugars. So what you do is you look at the last chiral center and look at the last OH. If the last OH is on the right, it's a D sugar. If the last OH would have been on the left, if it was on the left, so left versus right. If it's on the left, it's an L sugar. If it's on the right, it's a D sugar. Okay, so just to remind you of basic terminology in stereochemistry and introduce a few more terms. So L-glucose and D-glucose would be enantiomers of each other. If you remember, enantiomers are non-superimposable mirror images. So this is an L sugar because that's on last OH is on the left, or this is a D sugar because it's on the right. But L and D would imply they're enantiomers of each other, which means they have to be mirror images of each other, right? So you can't just change the last chiral carbon and call that the enantiomer. Every single chiral carbon has to be opposite. And so you can see that these are mirror images of each other. So every single chiral carbon is opposite in stereochemistry. If you remember what diastereomers are, so diastereomers would be, they're not mirror images and they're not superimposable. So if they're not the same, And if they're not enantiomers, but all of the atoms they're not constitutional isomers, then they're going to be diastereomers of each other. So these two are diastereomers. Why are they diastereomers? So let's see. So this chiral carbon's opposite, right? Because there's a mirror image there. This chiral carbon's the same, and this one's opposite. So those are opposite, and this one's the same. So if one of the chiral carbons is opposite and the rest are not, then they're not enantiomers, so they're diastereomers. So another term to know is epimers. So epimers are stereoisomers that differ in only one chiral center. So you can see that here they're the same, that's the same, that's the same, that's the same, but those are opposite. So they differ in one chiral center. It does not matter where the chiral center at, but if they only differ in one chiral center, they're epimers of each other. Okay, so the triose has one chiral carbon, so there would be two stereoisomers, right? So D-glyceraldehyde is the one that's shown. The other one would be its enantiomer. If you have a tetrose, then you have two chiral carbons, so four stereoisomers. So D-erythrose and D-threose would be two of them. The other two would be their enantiomers. Pentoses have three chiral carbons, so 2 to the 3 would be 8 stereoisomers. So 4 of them are shown, and the other 4 would be their enantiomers. And a hexose has 4 chiral carbons, so 2 to the 4 would be 16 stereoisomers, so 8 of them are shown, and the other 8 would be the enantiomer of these 8. So for the keto triose, there's no chiral carbons in this, right? So no stereoisomers there. And similarly, for the tetrose, now there's 1 chiral carbon, so the other stereoisomer would be its enantiomer. 2 chiral carbons for pentoses, so 4 stereoisomers, and the hexoses, 3 chiral carbons, so 8 stereoisomers. So the other 4 would be the enantiomer of these 4. Okay, so this is one of the most fundamental aspects of a carbohydrate, is that they, and this is a reaction that we've seen before back in the aldehyde and ketone chapter. So if you remember, if you take an aldehyde and an alcohol, then they can react with each other. Since this carbon's partial positive and oxygen's partial negative, right? Oxygen can attack the carbon and break the double bond O, and then oxygen picks up a hydrogen. So now you have a carbon with an OH and an OR group, and if you remember, that's what's called a hemiacetal. Or if it was a ketone, sometimes you see this terminology used. So same concept. Alcohol can attack the carbon-oxygen double bond of the ketone and break the double bond and make that an OH. So now a carbon that's got 2 OR groups, so it would be coming from a ketone. So instead of an hemiacetal, that's sometimes called a hemiketal. Okay, so of course with carbohydrates, these alcohols and aldehyde or ketone is in the same molecule. So if the alcohol reacts with the aldehyde or a ketone, then it's going to close up into a ring. And so we've seen this in organic chemistry, the aldehyde ketone chapter before. If you took a simple molecule like this, oxygen's partial negative, carbon's partial positive, so this can attack there to make a cyclic hemiacetal. So it could make if it makes a 6-membered ring, then that's what's called a pyranose. Or if it makes a 5-membered ring, then it would make what's called a furanose, right? Named after these molecules, pyran and furan. Okay, so biochemistry is basically just organic chemistry kind of on steroids. It's much more complex organic chemistry, but it's for the most part a lot of the same fundamental reactions. It's just a more complex molecule, right? But so if we take glucose, for example, it's just a polyhydroxyaldehyde. So they undergo similar reactions that aldehydes undergo, similar reactions that alcohols undergo. And so one of the fundamental reactions is making the hemiacetal. So we have 5 oxygens, 5 OHs in the molecule, so any of them conceivably could attack the C double bond O, right? If this one did, though, that would make a 3-membered ring, and that's not favorable. If this one reacted there, that would make a 4-membered ring, and that's not favorable. If this one reacted there, that would make a 5-membered ring, that is favorable. So making 5-membered rings, 5-membered rings are quite stable. Or if this one reacted there, that would make a 6-membered ring, and that's predominantly what happens. Or conceivably, you can make a 7-membered ring, but making 7-membered rings is less favorable. because then entropy becomes a factor. That OH is so far away, the chances of it finding the C double bond O once it becomes further away diminishes. But making 5 and 6 membered ring is very prevalent. So what we want to do is close this into a 6 membered ring, and we want to keep track of all of the stereochemistry of all of these chiral carbons. So what we're going to do is draw what's known as a Hallworth projection. So this structure is just the D-glucose drawn from a different perspective, right? So what we want to do is this oxygen here at the 5th carbon is going to attack there and close that into a ring. So when it does that, you have to recognize, so this carbon, the aldehyde, is not chiral, but when that alcohol adds there, it becomes chiral. So this OH could attack from the top, and then that would force this oxygen to the bottom. That would give this stereoisomer. So that carbon is now chiral. Or this OH could attack from the bottom, or it could attack from the bottom, and then that would force this oxygen to the top, and so that would give this stereoisomer. So when it closes into a ring, you create a new chiral carbon. So at C2, C3, C4, C5, nothing happens at those carbons, so the stereochemistry there remains the same, but C1 becomes chiral. So you create a new chiral center at C1, but C2, 3, 4, and 5 are all the same stereochemistry. So if we compare these two molecules, what kind of stereoisomers are they? So they only differ in one chiral carbon, so they would be epimers of each other. So they are epimers. And so a new term for you, they differ in chirality. So this carbon is called the anomeric carbon, right? That's the hemiacetal carbon. That carbon is unique, right? That carbon has 2 oxygens attached to it. So that's a unique carbon in the structure. It has an OR and an OH attached to it. That's a hemiacetal carbon. So when the stereochemistry differs only at the hemiacetal carbon, then those 2 stereoisomers are called anomers of each other. So anomers are a specific kind of epimer. They only differ in one chiral carbon, and they only differ in chirality at the anomeric carbon, right, the hemiacetal carbon. Okay, so when we draw this in a Hallworth projection, so there's an easy method to keep the stereochemistry correct. So when you draw a Hallworth projection, you always draw it like this, where this oxygen at C5 that becomes part of the ring is always drawn in the upper right-hand corner. And then you number 1, 2, 3, 4, 5 around the ring. Okay, so how do we get, so the stereochemistry at carbon 1 could vary. The OH could be up, right, or the OH could be down, because that came from the aldehyde carbon, which is not chiral. When the OH attacks it, it becomes chiral, but you have to get both stereoisomers possible there. But now how to get the chirality right at the other carbons? So there's an easy way to do this if you just remember this. So if OH is on the right in the Fisher projection, so that would be this one and this one. This one doesn't count because that becomes part of the ring. So these 2 OHs are on the right, so they will be down in the Fisher projection, right? So that's why. So the one at C2 is going to be down, and the one at C4 is going to be down, and then the OH at C3 is on the left, so it's going to be up in the Hallworth projection. And then what to do with the CH2OH? Well, if it's a D sugar, so this is a D sugar because the last OH is on the right. So if it's a D sugar, the CH2OH is drawn up in the Hallworth projection. And so then the hydrogen on that carbon would be down. C4, the hydrogen on that carbon would be up. 3, it would be down. And 2, it would be up. And then 1, it could be up or down, right? So when it closes into the hemiacetal form, you get 2 stereoisomers. So this will be something you would have to do on the last exam. I give you a carbohydrate in the open chain Fisher projection form, and you draw what it would look like when it's closed up into the Hallworth projection form. Okay, so but then it gets a little bit more complex than that, because the Hallworth projection, the molecule's drawn flat. So this is a 6-member ring like a cyclohexane. It's just got oxygen in it. And of course, you know cyclohexanes are not flat, right? They adopt chair conformations. So what we want to do is let's take this Hallworth projection and draw in a chair conformation instead. So let's remind you right quickly how to do the stereochemistry and then convert to a chair. So these two chlorines are cis, right? So if we put it into a chair, so this chlorine's on top of hydrogen and this chlorine's on top of hydrogen, so that would be cis. So if you notice, it's either 1,2 substituted, so this is axial and equatorial. And then if you did a chair flip, then everything axial goes equatorial, everything equatorial goes axial, right? So this will be the chair flip, which is still cis, because so that's equatorial now. So this went from axial to equatorial, and this went from equatorial to now axial, but they're still cis to each other. If it was 1,3 substituted, so 1,3, so now they're both on top of hydrogen, so they're cis, but now they're both axial. Or if you do the chair flip, they're both equatorial. And which would be more stable? Would be both equatorial, right? Because putting big groups equatorial gives them more space. So similarly, we could do the same thing for 1,3 trans. So this is on top of hydrogen, but this is on bottom of hydrogen, so that's trans. So if they're trans, one is axial, one is equatorial, or if they do a chair flip, one is equatorial, one is axial. And then if you went to 1,4 substituted, so cis, this is on top of hydrogen, this is on top of hydrogen, that's cis. So if they're 1,4 cis, something has to be axial, something has to be equatorial. Or if they're 1,4 trans, then, right, so this is on top of hydrogen, this is on bottom of hydrogen. So if you put that into a chair, they either both have to be axial or they both have to be equatorial. And of course, this equilibrium would lie far to the right, so because they prefer to be equatorial. So if we went to a more complex molecule, now you have 3 things on cyclohexane. They're all cis with respect to each other. So the way that I do this, let's just put the OH on first. And now that if we put that here, that defines where everything else has to go. So if this is on top of hydrogen, then the bromine has to be on top of hydrogen. So if this is axial, this has to be equatorial there. And then if you go to the 4th position, so if OH is on top of hydrogen, then chlorine has to be on top of hydrogen. That way they are cis, right? Since they have to be cis here. So with respect to each other, they're cis and cis. So that would give you this conformation where one group is axial and 2 is equatorial, or if it did a chair flip, then 2 would be axial and 1 would be equatorial, and the equilibrium would favor this, right? Okay, so if we did the same thing for carbohydrate, now you have every single carbon is chiral. So this first carbon doesn't matter, right? The OH could be here or it could be there, axial or equatorial, because that carbon, you get both stereoisomers there. But then the next one, so let's see, so what do? So we put OH, well, here's the simplest way, right? So H is on top of OH, so H is on top of OH. And then OH is on top of H, so OH is on top of H. And then here H is on top of OH, so H is on top of OH. And then similarly for the CH2OH, it's on top of hydrogen in the Hallworth, so it's on top of hydrogen in the chair form. Okay, so so this is the open chain form. It's just drawn in the conformation so that you can easily see that this attacking there to close. So when it does this, again, it could attack from the top or the bottom, so you get either of these stereoisomers. So some new terminology for you, right? The alpha and the beta form. So what you do is you look at the OH at the anomeric carbon and the CH2OH. So if they are cis, so the OH and CH2OH cis, that equals the beta form. And I think that was defined. Was it defined earlier and I just skipped it? Maybe not. Or if the OH at the anomeric carbon and the CH2OH trans, and that's what's called the alpha isomer. So more terminology to know. So which one is more stable? Well, if it's beta, they're all equatorial. And so that's the more stable form. So you can see that here, that you get 62% in the beta form and only 38% in the alpha form. But this carbohydrate is constantly going between all of these forms. It'll close into the alpha form and then open back up. Close into the beta form and then open back up. Or it could close into the 5-membered ring, right? And you could make the furanose. And then open back up, close into this furanose form, where again the only difference is the stereochemistry at that anomeric carbon. So glucose in solution is a mixture of all 5 of these, but it primarily looks like the beta D glucose pyranose form, because that's thermodynamically the most stable with all of the groups in the equatorial position. But in that process, so another term for you is what's known as muted rotation. So that's where it's opening up. So that's where it's closing into a pyranose or a furanose, and then opening back up, and then closing, and then opening back up, and so forth. So you can measure the optical activity of these, right? So this has an optical activity of plus 112.2 degrees. This is plus 18.7. Those are not enantiomers of each other, right? They're diastereomers of each other, so they don't have equal and opposite optical rotation. They have different optical rotations because they're diastereomers of each other. Okay, so this just kind of summarized that. If you have the pyranose form, right, it could be in a boat conformation, but it prefers the chair conformation. So some derivatives, so all carbohydrates do this. So this is just showing this for D-ribose. So D-ribose could close into a 6-membered ring, or it could close into a 5-membered ring. And so which one is favored for ribose? The beta pyranose form is favored. Okay, so reducing. So if we look at a little bit of the reactions of carbohydrates, so some more terminology. So reducing sugars. So reducing sugars, right, there are sugars that can be oxidized, and so something else gets reduced. So when in the uncyclized form, so when they're cyclized form, they're not susceptible to oxidation. But when they're uncyclized, you have an aldehyde, and you know from the aldehyde and ketone chapter that aldehydes can be oxidized. Ketoses can isomerize to aldehydes, and they can be oxidized by that process as well. So this is just a few of the reactions that show some of the oxidations of aldehydes and ketones. So that's an aldehyde, which can be oxidized to a carboxylic acid. So you can use a reagent called Benedict's reagent, which is copper sulfate, sodium citrate, and sodium carbonate. So copper 2 is blue, and so when the aldehyde gets oxidized, the copper gets reduced. If you remember from general chemistry, the definition of reduction, so it's the gain of electrons. So its oxidation state goes from +2 to +1 when it gains electrons, and it changes the color of the copper. So that would be one way that you could test for a sugar, is use this reagent and watch the blue turn to red in this case, and how fast that changes and how significant the color change is will give you an indication of how much carbohydrate is present. So some of the same reagents that we looked at in the aldehyde chapter will work here, right? You can use Br2 in water, and that'll oxidize the aldehyde to the carboxylic acid. We've looked at this reagent, that's what's called Tollens test, where the silver 1, right, gains an electron and becomes silver 0. So when the aldehyde is oxidized to the carboxylic acid, silver gets reduced, and so you see a mirror forming as the silver 0 precipitates out of the solution. Or you can oxidize it with nitric acid, but in this case, both the aldehyde and the last free primary alcohol gets oxidized to carboxylic acids. So a few other reactions of carbohydrates. And so again, it's some of the same fundamental reactions that we've looked at for simple organic molecules can do some of the same chemistry on complex molecule like a carbohydrate. So aldehydes can be reduced, right? Sodium borohydride will reduce the aldehyde to a primary alcohol. Or you could do hydrogenation, right? H2 and then some metal catalyst will reduce the aldehyde to primary alcohol. If you take an aldehyde, if you remember this reaction, Cn minus would attack here. That becomes an O minus, which picks up a hydrogen, and so you can make a cyanohydrin. So this would be a way that you can extend the carbon chain by 1, and then you could do chemistry on the CN group. You can convert that to a carboxylic acid, for example, and then you've extended your carbohydrate chain by 1. Of course, when this happens, this carbon is not chiral, but it becomes chiral in the process, so you would get both stereoisomers there. If you take a carbohydrate, so a hemiacetal with another equivalent of alcohol, if you remember what can happen there. So this can protonate to make water, and then water can leave, and then another alcohol can come into its place, and so you make this, which that's now an acetal. Or in carbohydrate chemistry, it's called a glycoside. All right, so that would be analogous to this reaction that we've looked at. Right, in the carbohydrate chapter. Take an aldehyde with 2 equivalents of alcohol, then, well, the first equivalent of alcohol was that oxygen closing up, reacting with the aldehyde to make the hemiacetal, and then if you reacted it with a second equivalent of alcohol, in this case an external source of alcohol, then the OH can leave as water, and another alcohol can react there to make the acetal bond. Right, acetal has 2 OR groups attached to it, and that's called a glycosidic bond in carbohydrate chemistry. Okay, or if you reacted these alcohols with a good alkylating agent like methyl iodide, right, then you can make ethers, and of course you just have lots of alcohols. So instead of doing that reaction once, you would just do it at all 4 of those alcohol positions that are open. Same if you take an alcohol, we looked at this in chapter 21 with an anhydride, right? So that's not the mechanism, just a way to think about the product. The alcohol attacks, kicks off a leaving group, and then you would make an ester bond. So you could do an esterification, and then of course you have 4 alcohols, so you would just do the reaction 4 times if you 4 equivalents of the acetic anhydride. Okay, so lastly, just a few derivatives of carbohydrates. So carbohydrates are phosphorylated commonly, so they could be metabolic intermediates. So if you take biochemistry and study metabolism, you'll no doubt run across these at some point in those studies. And of course this one, if you attach a nucleol base to a carbohydrate and phosphorylate it, so in this case you formed adenosine triphosphate, or ATP. So you find carbohydrates as components of other biological molecules, in this case nucleic acids. So deoxy sugar, so this is ribose, this is 2-deoxy, so this would be carbon 1, that would be carbon 2, right, if you were naming this. This would be 1, 2, 3, 4, 5, so that would be what, 2, 3, 4, 5, trihydroxy, pentanal, a technical name, but carbohydrate chemistry would just be called ribose. So 2-deoxy would mean it's missing the OH group there. So where do you see deoxyribose used at? DNA, right? What does the D stand for? It stands for deoxyribose. So deoxyribose, nucleic acid. So other derivatives of carbohydrates where you're missing an OH group. So this would be rhamnose, so where that's found in bacteria that cause tuberculosis. Fucose, this is commonly found in cell surfaces and in meat glycans. Amino sugars, so commonly find the second carbon replaced with nitrogens, and these form important biological molecules such as glycoproteins and gangliosides. Find them in antimicrobial agents. Sugar alcohols, so we talked a little bit about sugar alcohols, I just didn't point it out, but if you take this aldehyde and reduce it to an alcohol, now they're all OHs, so now it's just a it's just a bunch of OHs, that's a sugar alcohol. So where do you find sugar alcohols? utilize that. Well, they can be artificial sweeteners. So sorbitol is an artificial sweetener that has 60% of the sweetness of sucrose, which is table sugar. Okay, and that's it for this first part of chapter 23. So the main focus of this chapter would be for you to know these basic reactions of carbohydrates, and for you to know how to take a carbohydrate and draw it as a Hallworth projection, and then take that Hallworth projection and be able to draw it as a chair in the chair form. Okay, we will stop there.